Good afternoon, this is Schweitzer, and we are looking at a video here, so some basics of ionic compounds. Sometimes I might refer to this particular section as, critical information that you literally need to breathe in this particular chapter. I will try and emphasize the things that are super important and the small details that maybe, could be let go and not worry too much about, okay? But how do I know if a substance is ionic? Okay, so this is pretty critical. All the naming systems and all the stuff is based off the type of bond. All the properties are based off the type of bond. So knowing right away if you see a molecule, I'm thinking that's ionic, that's important. So an ionic compound, first of all, is a metal and a nonmetal. So metal, all right, and a nonmetal. How do you know if a molecule is a metal or a nonmetal? Well, this little divider line right here, this side's metals and this side's nonmetals. This little divider here, aluminum would be a metal, and these are all metalloids as you're coming across here. So understand the divider between, metals and nonmetals, which is right here. All right. All right. Well, as you dig deeper, you'll realize we really have a cation, okay, and an anion. And we could often write the charge above it, +1, -1. There's a whole list of ions that we got to know the charges of, just kind of as part of our vocabulary. But there's this thing here, this one right here, okay, it's a little different, where we have a multi-atom anion. This guy's +1, this guy's -1. So in this situation, we have what we call a monatomic, and we have a polyatomic. The monatomic is a single atom, single atom ion. There's lots of these. Anything on the periodic table is single. All right, remember this is all +1s, +2, +3. This is teeter-totter, +4. You'll notice that lead and tin also form +4s. That's because of the family they're in. -3, -2, -1. Those are all your monatomic anions and cations. But we have this whole list of also multi-atom ones. This one's called nitrate. There is a whole sheet of these that are so common that you would difficult not to know a lot of them. But, sometimes in honors chemistry we'll do a little bit of memorizing these, just try and pound them into our working vocabulary quickly so we can use them. But, all right, so do you see one of these guys, metal up front, polyatomic ion, that you recognize? If you don't even recognize it, so you don't know enough even to know to go to your ion sheet, there's a problem. You're going to really struggle here. So let's just say we have an ionic compound. Okay, now ionic compounds, this particular deal is going to come out. How? I mean, because it's one of the main properties, and in this presentation you'll see us talk about this, is that it's a bulk crystal. It's really just a pile. Okay. Sometimes I'll take for example, if we have a bag of chips, sometimes I use gardentuos as an example because there's all sorts of different types of you got these little pinwheels, sticks, and you got other things, and I think there's like 4 of them, different types of things in there. How would you tell someone the composition of that bag? You're going to tell them how many of those little pinwheels are in there, how many sticks? Not really. And if you're in production of these things, there's a really precise amount of actual items in here. Those little cardboard looking brown discs and gardentuos, which are nasty, by the way. All of a sudden you got a bag and it's like 80% of those little brown discs, then you're like, oh, this stinks. Never that way. It's always the same kind of ratio. So they know the ratio. They don't come out and tell you. They know the ratio. Same thing here. How would you tell them? How would you tell this? And they just simply use what we call a ratio. All right. So they're going to do a ratio, and this will come out in our notes later on here. And we would do the simplest ratio, really. They're just going to tell the ratio of the big circles to the little circles. Okay. Now, of course, that's a formula, so we'll put that over here. Okay. So big circles to little circles. Okay, they're going to tell you, maybe there's 1 to 1, maybe there's 1 to 2, whatever ratio it is. Okay, and then how would you give it a name? other than Gardenchos for your little bag of chips. We're going to give this a name. So there's literally billions of these little circles and things. So they're just going to give you literally the name of this guy and which is the cation or the anion, and they're going to give you the name of that guy. So it's really important to realize that in this thing, I'm not saying it's the best way, but for an ionic compound, early on, they decide this, okay? They're never going to give you the quantities. Even though the formula, they're not going to give you the quantities, and they're not even going to give you the ratios in the name. I'm assuming it's because early on they didn't know it. And this is something that just sort of lagged on from the past. Even though the formula gives you the ratios, all right, they're not going to give you the quantities or the ratios. So whenever you go from the name, which never gives quantity ratios, to the formula, then you're going to have to generate that ratio or drop the ratio. All right, so let's get a little more detailed into it. Okay, now names. Okay, this is not in your book here, but a couple things about names. Name of cation and name of anion. So cations, individual monatomic anions, like say Al, okay, aluminum's a +3 charge. We just call it aluminum. Okay, we don't call it anything special. The rest of the world calls it alumininium, by the way. We call it aluminum. The name anion, not anions, we actually give special names. This family here is a -3, this family is a -2, this is a -1. So we give these names special endings, which just ends in "ide." So for example, Br-1 is bromide. Sulfide. Sulfide is just the negative form of sulfur, which is S-2. So be aware that we give a special name to the actual anions. Oxide is O-2. So, all right, names for formulas and name. We ever gave the formula, but or the naming convention, which is just name of cation, name of anion. How do we have a formula? First of all, just by general, we do the cation first. Okay. Then we want to make sure that our positives equal our negatives. Okay. So in this situation, what happens here? Well, we know that we have our metal. Okay, let's say for example sodium metal gives electrons to form Na+. It's going to give away electrons, but then the chlorine is going to take them. So because it's the same electron to form Cl negative, this guy can't produce any more positive than it can produce negative. So our charges have to be equal. Sometimes I make the analogy that if on Earth someplace you have a large hole, then you should probably, someplace there's likely going to be a pile. All the piles equal the holes. Someone dug a hole out, there's a pile. So all your positives and negatives are generally equal. Or not generally, they are equal. And at the end, because this is ionic, we want to make sure it's empirical. Okay. All right. So let's try some examples. Okay. Again, what does empirical mean? Simplest ratios. We'll review this as we move along here. Okay. So how do I give them a name? All right. Well, magnesium fluoride. All we do is, again, there's a couple ways you could do this, but typically we're going to take the charge, magnesium, and fluoride. This is a +2 charge in nature. This is a -1. How many fluorides does it take in order to make my charges equal? It takes 2 of them. So this is going to be MgF2. MgF2. All right, well, this is kind of mimicking what we call our crisscross rule. We take the Mg +2, the F -1, charge balance, the 2 goes there, the 2 goes there, the 1 goes here, and we get MgF2. Okay. Again, that's just a little technique. Does it work all the time? No. Let's look at iron oxide, iron 2 oxide. So that means Fe has a positive 2 charge. That's there because there's more than one version of iron. Oxide is an O negative 2, which is of course why I chose this, is to mimic when this does not work. All right, so if you charge balance this, you get Fe2O2. This is showing a pretty large neglect or understanding of that we actually just have a bulk crystal that is just full of piles and piles and piles of these things, and they're just cations and anions. There's no grouping, it's just a pile. Do we have a grouping of 4 atoms that simply repeat themselves over and over and over again? The answer is no. They're just individuals. There's no special O2. So what we want to look at this in terms more or less is, okay, I have Fe, which is a positive 2 charge. I have oxygen or oxide, which is -2. How many oxides will take the balance off the iron? Just 1. So this is FeO, and that's my answer. Or at the end, you should reduce it down to empirical. Do not let it not be empirical. Okay. I'm going to change this one to just sulfate. So that will be changed in yours eventually. All right, just because it's a better example. Okay, so aluminum sulfate. This is an example where we're going to use parentheses. So aluminum is going to be +3, and then the sulfate, SO4 -2, and we got to charge balance. A nice example, just using the charge balancing. So the 3 goes here, and I need 3 of these whole packages. I cannot change that. I know I just talked about reducing down, but that SO4 is a whole package that's never going to change. The -2 goes here. So this thing is going to be Al2 parentheses SO4 parentheses 3. Is this empirical? 2 and 3 are empirical. Cannot be reduced down. All right, these two. Why did I choose these two? They're going from a name back to a formula. I'm going to give myself a little bit of room here. This last page I had some room. So here we go. I got CuCl2, CuCl. If I just give the name of the cation, okay, and the name of the anion, I would have copper chloride. And that would be the name of both of them. Well, that's a problem here. And that is because, they're the same name. So, and it never gives quantities. So it's not like we want to tell that there's two chlorines here, because really they're not connected. This is just a ratio that's being repeated over and over again inside the crystal. They're all individual. So in this situation, I need to tell the name of this thing. We call this guy copper 2 and copper 1. That's literally the name of this thing, copper 1 and copper 2. So because there's more than one version, they indicate the charge. Okay. The most common options of these guys, and there are lots of them, ones that I don't know all of them, but Cu +1, +2, and iron is +2 and +3. This is probably the most common ones used. Are there other ones? Yeah, lead, for example, gold, +2, +4, pretty common, or somewhat common. All right, so this is how we're going to give these things names. Obviously, there's some practice sheets. You got to really be good at this. In order to breathe, you have to be able to do this stuff here in chemistry. Okay, so in the end here, let's take a little closer look. I don't know if this is just important to understand, I guess, a little bit in background information, not like super common, but just understand this is the background of how these things are actually made. Okay, I'm going to walk through one example of this, and you can try one on your own if you'd like. It's not super important, I guess you might say. Not something that I'm going to sit and spend a ton of time on. I'm just do one example, and you can putz around with it how you want. But how are they actually? Why are they charge balanced? What happens on a molecular level to make them charge balanced? Okay, it doesn't just happen. We know that the aluminum is going from aluminum. I kind of talked about this already, and chlorine. So how do we get to this ratio? Okay. Well, we have aluminum. I'm just going to do it like this. Aluminum goes to aluminum plus 3. And this is 3 electrons, by the way. Okay. Now I have chlorine. Now this is the part that makes the math just look a little bit funnier. If this 2 wasn't here, you'd see this proportion come out much quicker, and it'd be much easier. With that being said, Cl2 goes to 2 Cl negatives. And there's picking up 2 electrons, 1 each. Okay. Now, conservation of electrons means whatever's lost here has to be gained here. So this guy's going to multiply times 2. This whole thing is going to cycle through twice to lose 6 electrons. 6 electrons, 2 aluminums, 2 aluminums, times 3. Again, that's going to give me 6 electrons, but it gives me 3 of those and 6 of these. Let's put everything together. I got 2 aluminums, metals, are losing 6 electrons, plus 3 chlorine molecules, both of no charge, to produce what? 2 aluminum plus 3s plus 6 Cl negatives. Now remember, this bulk crystal is just a stack. It's not like they're connected in it. We're just telling the ratio of what's inside here. Okay? And there's 6 aluminum, 2 aluminums for every 6 chlorines, and the simplest ratio here is AlCl3, and that's the ratio that happens here. This is a really long way. A lot of good stuff here that we will use eventually in these techniques of half reactions and balancing. But right now, this is just an idea. You can try your own example here if you'd like to see how it works out. You know it's going to be, the end result is going to be plus 2, minus 2, so 1 and 1, all right, and then just plus 2, minus 2, that works out. That's the formula. But you can break it into half fractions and look at it if you like. Understand that's where it comes from. Okay, now here, again, who's being oxidized? The barium here is going from barium to barium plus 2 electrons. Anytime you're on the product side, you're oxidation. And then you have the nitrogen is going to N minus 3. Of course, there's 2 of them here. So how many electrons this guy? This guy's going to gain, let's N2, because it's diatomic. So that's like a bunch of electrons, 6 electrons each. And you can go through your whole ratio here. You're going to see eventually you're going to get a 2 to 3 ratio here. Okay. The short way would be barium nitride. This is a plus 2, minus 3. 2 of these, 3 of these gives us a total 3 here, 2 here. Would give me a plus 6 and a minus 6. Again, our charge is balanced. Eventually, when you balance the electrons up, you'll get back to this 3 to 2 ratio. Either way, this is underground information that is just something to be understood and thought of. All right, why are compounds always listed in empirical? All right, again, let's reiterate that, is that essentially we have a big stack, and how else are you going to describe these, okay? We just list the simplest ratio. Empirical is the simplest ratio of atoms. We do it simply out of necessity. Are they molecules? Are these things stuck together, in a simple ratio? No. It's just a stack. So there's 1 to 1. This pattern right here is being repeated over and over and over again. This little unit gets repeated over and over again, and they actually call this a formula unit. Okay. Again, reminder again, okay, empirical formula, we just mentioned that. Best way to describe composition, all right? This bond right here is actually an ionic bond. Very strong. When melted, it's what breaks. So bulk crystals, one of the most interesting properties, or the most unique properties of this, is just that it's a bulk crystal. Okay, and it's empirical. This is the ionic compound right here. This is what breaks. So it's such a strong bond that it is likely a solid at room temperature, and likely solid at pretty much almost any temperature on Earth, definitely on the surface. Okay. Bulk crystal, one of the most commonly tested, it has to be understood properties of ionic compounds. They're not molecules. Okay. So again, simplest ratio. Keep that in mind. All right, and that ends our video here. Thank you very much.